Thanks, John, and thank you everyone for tuning in today. As John said, my name is Nick Capelli, and I'm a Senior Application Engineer here at Parker Lord. And today we'll be going through TM401, Epoxy Properties. On today's agenda, we have many different topics, starting with what is an epoxy and where are they used? 2K versus 1K epoxies, Epoxy TG and CTE, commonly used epoxy thermal management solutions, and finally, we'll end with epoxy products and applications. And just as in the previous 3 thermal management discussions, feel free to join the conversation on Twitter using the hashtag thermalmanagement401 to share your thoughts or join in on the conversation. And as always, please do follow us at Lord Corporation. So speaking on Parker, and as we mentioned in the last 3 presentations, we are a very global company, but with a local focus. And as discussed previously, most of the materials that we will be discussing today are made in Indianapolis, Indiana, Sagertown, Pennsylvania, Hochhofen, Germany, or Shanghai in China. Again, speaking on our expertise, most of what we see in applications will be the transportation section, planes, trains, and automobiles. But of course, we do have other markets which we're involved in, as well as a number of different key products that fall into these markets. However, today's focus will be mostly on thermal management, electronic materials, adhesives, and coatings. So you've seen this slide previously in TM301, and now today's focus will be moving from silicones to epoxies. So let's talk more about those. What are some of the characteristics of epoxies? So first we'll talk about where epoxies are used. Epoxies are going to be found in a lot of everyday household applications, like floor coatings and sealants, countertop or table coatings and sealants, industrial coatings, circuit board potting materials, primers and paints, other structural adhesives like the Lord 310 pictured here, and then finally in reinforced resin boards that can be used for making different applications. So then what is an epoxy? An epoxy is named for the epoxide functional group, which is found there in the top right corner of the slide. As you can see, it's a triangular shaped ring with an oxygen at the top. As far as what kind of polymer an epoxy is, you've probably heard of 2 different polymer classifications. You have thermoplastics and thermosets. Thermoplastic materials are polymers that will cross-link, and then they can be melted down once heated to form back into their original shape. Whereas a thermoset, which is what an epoxy falls under, is a polymer that cross-links, but once it has been cross-linked, you can't heat it up to then be melted again. Often the term epoxy is used as a catch-all term to include really any thermoset material that you could find at a hardware store, like a paint, like a coating, like an adhesive. But it's really important to understand that not all of these materials that we call epoxies are actually epoxies. And then on top of that, not all of them have the exact same properties. But we'll be talking about that more in the coming slides. So starting with 2K versus 1K epoxies, we'll start with 2K. 2Ks are probably going to be the more common things that you'll see in a hardware store, the easily convenience packaged adhesives. These 2K or 2-component epoxies have an A side called the resin and a B side called the hardener. Typically, these materials are cured at room temperature, and that's because a lot of these 2K epoxies are used for everyday household applications. So it's a lot easier for the average person to have something cure at room temperature as opposed to finding an oven that they can dedicate to cure the material. You can, however, use heat to accelerate or speed up the cure of these materials. And in addition, sometimes heating up the material can raise the TG, which can improve the performance at higher temperatures. Looking at 1K epoxies or 1-component epoxies, these materials may be premixed. So you would take the resin side, the A side, and the hardener side, the B side, mix them together and put them in a syringe. Then to prevent them from reacting, unlike the typical 2K epoxy, you would put them in frozen storage to ensure that they won't start reacting until you're ready to use them. These materials typically will be used with a heat cure, and that's because they're going to be used for higher performance, And they also typically will use latent curing agents. A latent curing agent is essentially something that's added to a formulation that significantly slows down or prevents the cure of the material until a certain amount of energy is input into that epoxy. So it takes a lot of heat for that latent curing agent to activate so that the material can start cross-linking and curing. Additionally, some one-component epoxies instead will use a cationic UV cure, which allows for cure to be very, very quick. So looking at the advantages and limitations of epoxies, we'll start with the advantages. Epoxies do have a very convenient range of cure temperatures. You can cure as low as room temperature, and then some epoxies can cure as high as 210 degrees Celsius. Now, your curing temperature is going to be dependent upon your application needs, and we will talk about that more later with some specific examples. Epoxies also form no to few volatiles during cure. They generally have excellent adhesion. Filled epoxies are notable for their low shrinkage during cure. Unfilled epoxies, not so much, but as you start adding more filler, the dimensions of the epoxy won't change as much during the curing process. And finally, epoxy materials are very environmentally and chemically resistant. And this is possible because epoxies have a very high cross-link density. Because of this cross-link density, it makes it difficult for things like solvents, other harsh chemicals, rain, dirt, dust, other types of debris to fill in and penetrate through those spaces in the cross-links. So this is why epoxies end up being such a great environmental barrier. Looking at limitations, of course, some of the advantages that we've listed here actually lead to these limitations. Speaking first on poor repairability, most of these epoxy systems are non-repairable or non-reworkable, and that's because they have such excellent adhesion. So oftentimes we'll actually have customers come to us and say, we would like to use one of your epoxy potting materials for a circuit board, but we have some really great IP on that circuit board and we don't want our competitors finding out what it is. So we want an epoxy that is going to stick very, very well so that if they try to reverse engineer our circuit board, they end up breaking the circuit board by trying to peel away the epoxy instead. Also, again, due to their great adhesion and their rigidity, epoxies tend to be fair in thermal cycling and thermal shock. And this is because their rigidity can cause cracking if something gets too cold, as well as depending upon where your glass transition temperature is within the operating temperature, you may be crossing over the TG as the material cycles thermally. And if you keep doing that, that puts a lot of stress on the potting material, the adhesive, or whatever you're using, which could lead to cracking and ultimately may cause failures in your application. As I've mentioned already, most epoxy formulations are relatively rigid and brittle. And then finally, some of these epoxies don't have very great UV resistance. There are some, however, that can be put out in the sun for years and years and years with no degradation of performance. But in general, those are going to be limited to the all aliphatic epoxies. So let's talk now about Epoxy TG and CTE. As I mentioned earlier on the last slide, TG can be influenced by the curing temperature. So at least in our Cooltherm portfolio, most of our epoxies, when even they're just cured at room temperature, have a TG of at least 50 degrees Celsius. However, most of our customers are interested in higher performance at high temperatures. So to counteract this, what they'll do is bake the epoxy at a higher temperature, typically 10 to 20 degrees above their operating temperature. That way the TG will be very close to the upper operating limit of the application so that the properties remain consistent and the material remains rigid throughout the entire operation. Now, related to TG is CTE. CTE is something that changes with temperature, especially below or above the TG. So for applications that are very sensitive to expansion or contraction of the potting material or the adhesive or whatever kind of epoxy may be used, it's important to maintain a lower or smaller CTE. Below TG, the CTE remains small. So for these applications, people are typically interested in keeping their TG high, so their CTE is kept small. Changing in CTE from a smaller number to a larger number which can lead to cracks during the thermal cycling or thermal shock performance. And also, whenever substrates are changing or expanding or contracting at different rates because they have different CTEs than the epoxy materials that are in contact with them, that can actually lead to delamination of the adhesive, the potting material, or whatever kind of epoxy is being used, which will ultimately prevent the epoxy from functioning like it should. So it's really important to be able to match the CTE of the epoxy with the components and the substrates in the application. Moving to epoxy thermal management solutions, we see two major classifications of materials in this space. The first will be the potting and encapsulation materials, which are pictured in the motors on the right. These are typically used in battery applications, electric motors as seen here, magnetics, and then general PCB potting to help transfer heat away from those coils or the hot electronics within the applications. In addition, these materials are providing dielectric protection, environmental protection, and a bit of added structural support to the application. Also, we do have coatings, and as you can see here in this picture, this is what a coated heatsink looks like with an epoxy coating on it. These are typically used with heatsinks, or sometimes as conformal coatings on PCBs. In general, these coatings are used to provide excellent dielectric strength where high voltage applications are present, or environmental and corrosion protection. We do also see two more types of thermal management solutions, and these are adhesives and underfills. In adhesives, we typically see three different types of thermal management solutions. There are structural adhesives, which can be used to help assemble battery packs and enclosures, or connect hot electronics to a heat spreader or heatsink. We have die attach adhesives, which are pictured in the picture on the far right, that are both thermally and electrically conductive, used to adhere dies to the inside of semiconductor packaging. We have surface mount adhesives, which are used to replace wire bonding on PCBs by adhering components directly to the PCB and helping to transfer heat when necessary. And then finally, we have underfills. Looking at underfills, you can see here on the picture on the left, these are meant to help encapsulate underneath semiconductor packaging and provide some sort of extra structural support, as well as some environmental shock protection for these components. So let's get more into the detail of the epoxy applications and products. You can see here we have a number of different applications where epoxy can be used, from things like electronics to industrial applications, LEDs, motors, and transportation. So let's dive into the Parker-Lord epoxy portfolio. As you can see here, we have four major classifications of material in the Parker-Lord epoxies: coatings, microelectronic products, potting and encapsulation, and finally structural adhesives. As you can see in micro and in potting, we have a number of different subcategories. Let's start first with Lord JMC 700K dielectric coating. This is the most popular epoxy-based coating that we offer at Parker-Lord. And as you can see, it's used to coat heat sinks, as well as used to coat permanent magnets on electric motors. In addition, you could also use this coating to apply to the inside of battery boxes or housings in battery pack applications. The main purpose of this material is to be used as protection against corrosion, against high heat, and then also to be an insulating layer electrically on your application, especially where high voltage is used. This way you're not concerned about current arcing somewhere that it shouldn't. This coating is typically spray applied at 75 to 100 microns and then cured at 180 C for 30 minutes. Moving to our microelectronics products, there are three different subcategories that we offer in microelectronics. First, we have adhesives, second are encapsulants, and third are underfills. Starting with adhesives, we'll typically see these epoxies used for die attach applications, surface mount applications, and or general TIM applications where thermal conductivity is needed to go from a component to a heat spreader or heat sink. These materials are typically 1K, pre-mixed and frozen, so then they require a heat cure to be used. Of these products that we offer, I think our most popular is probably Cooltherm MD140 SP, which is a thermally conductive and electrically conductive die-attach adhesive. Moving to encapsulants, these are going to be similar to the larger scale potting and encapsulants that we'll talk about and you've heard about in some previous presentations. But instead of being for an entire PCB, these will be used for just individual components on the PCB. Some neat applications that you can do with this are to use a thixotropic dam to actually create a barrier around the component and then fill in that dam with the actual encapsulant. We have a perfect example of this type of application with thermoset ME455 and 456. These are called our dam and fill products. And finally, we have underfills, which we've mentioned a little bit before, but they are similar to encapsulants, just used for underneath the individual components. They do help provide structural support and adhesion to the PCB. And I would say that our most popular product in this line is Cooltherm ME525. Moving next to general purpose potting, these are those larger scale potting applications that I was mentioning in the last slide. Typically, these types of materials are low to medium viscosity, environmentally resistant because they are epoxies, have good adhesions to both plastics and metals. They're typically 2K room temperature cured, and then they may be unfilled or lightly filled depending upon the needs of the application. As I mentioned before, adding filler can actually help increase the TG as well as decreasing the CTE of the material. Typically, we see these materials used in things like connectors, relays, and sensors. And our most popular products that we offer are Lord 600, Thermoset 300, and Thermoset EP20. Let's talk next about ignition coils. An ignition coil is a transformer, essentially, that takes voltage from a battery and then sends that current through winding after winding after winding, and then transforms it into about 30,000 volts to ignite the fuel in the end application. As you can see in the below picture, there are these larger copper windings at the bottom. But what's really important to notice is that in the section that's right above it, you have more copper windings. These windings, however, are very, very, very tiny. If you look really closely, you might be able to see the spaces in between them. For an ignition coil to be successful, the current must travel in one continuous path, and it cannot jump from wire to wire to wire. So when potting an ignition coil, it's really important that the material fills in between every single space, nook, and cranny in the application so that it has perfect dielectric protection from one coil to the next. As a result, the materials that are required for ignition coils have to be very low viscosity, have to be very high in dielectric strength, and then because you can see how small those windings are, the potting material needs to not break them if it's expanding or contracting. So these ignition coil materials typically have very low CTEs and very high glass transition temperatures, so that even at very high temperatures within the application, the material still isn't expanding or contracting too much, so that it doesn't risk breaking the wire. In addition, of course, some of these materials are going to be exposed to oils or greases, so it's important that the ignition coil potting materials are environmentally resistant, which is why epoxies are typically the material of choice. For these applications at Lord, we typically see Lord EP809, Thermoset ES111, or Thermoset ES121 used. Moving next to motor potting. Motor potting is going to be very similar to ignition coil potting, but it's almost like you put the ignition coil materials on steroids. For these kind of materials, you're going to be having some of the same properties. A low viscosity to be able to penetrate all the spaces between the windings. Environmental resistance will be a must as well, because motors can be exposed to oils and greases and other things in the environment. Again, a low coefficient of thermal expansion, because you don't want to damage the windings. A very high glass transition temperature, again, because you want to retain your properties through the entire operating range. And then a very high dielectric strength. Of course, again, because the current needs to travel in one continuous path. In addition, though, these motor potting materials are typically used in applications that can see operating temperatures up to 180 C, 200 C, sometimes even higher than that. So it's important and imperative, really, that these motor potting materials have TGs that are above 200 degrees Celsius. And on top of that, because motors are generating a lot of heat, it's really important that they're thermally conductive materials inside the stator so that they can transfer the heat out of that stator and then transfer it to the housing to be left elsewhere so that the motor can operate at a proper temperature. So the most popular products that we see used for motor potting at Lord are the Cooltherm EP2000 and the Cooltherm EP3500. So let's dive more into the benefits of electric motor potting. We'll start first with higher power density. You can see this by looking at the graph on the right or in the pictures below. If you take two motors of the same size and then you have one that's potted and one that's unpotted, you can get more horsepower or torque from the potted motor. You can see this in the pairing of motors on the right side. The unpotted motor, which is on the left, has 15 Newton meters of torque while operating at ADC. But the motor on the right, which is potted, has 17 Newton meters of torque while operating at ADC. In addition, you can also see the same torque or horsepower from a smaller motor. So looking at the pair in the center, you can see that you have two motors, both operating at 15 Newton meters of torque, but one is significantly larger, and that's the unpotted motor, whereas the potted motor has an overall smaller diameter, it's going to be lighter, so it will ultimately save you weight and money in using the raw materials to make the motor. Next, talking about better reliability, having a potting material inside the stator of the motor allows the overall motor temperature to be lower when operating at the same power. Again, you can see this in the graph on the right, or looking at the pair on the left, at the bottom of the slide, you can see that you have an unpotted motor, which is operating at 15 Newton meters of torque, and the operating temperature right there is 80 degrees Celsius. Whereas the potted motor is operating at 15 Newton meters of torque, but its operating temperature is only 65 degrees Celsius. In general, the rule of thumb with motors is that for every 10 degrees Celsius you decrease the temperature of the end windings, you can double the lifetime of the motor. So for anyone who's an end user of a motor, having a motor that's running cooler means they have to spend less money on motors over time. So that's going to be a big benefit for motor consumers. And then finally, the last benefit of motor potting is going to be that you can lower your copper losses at lower temperatures. In this case, that means there will be less resistance to the current flow, so that you're not going to be losing as much energy to heat. And finally, discussing thermal potting. These are going to be materials that are used typically in power electronics, like converters or inverters. Sometimes, however, you also may see customers use these in battery packs that they don't want to be serviceable. In general, thermal potting materials are going to be low to medium viscosity, environmentally resistant, of course, thermally conductive, and will typically have a low coefficient of thermal expansion. The most popular products that we see used in our line of thermally conductive epoxies, in addition to the motor potting materials already mentioned, are Cooltherm EP340, Cooltherm EP6007, Cooltherm EP6009, and then Cooltherm EP6035. The trend here is the same with motors. If you have something operating at a lower temperature, it's going to allow your electronics to last longer and function properly. So everyone is trying to get more power dense electronics. Therefore, they need more thermal conductivity to transfer the heat out of their application. And finally, here's a table of some of our most popular epoxy products, all of which have already been talked about today in some detail. But this is just a nice reference slide for you to see more of the detailed properties of these materials. So key takeaways from today, let's go over them. First, it's important to remember that epoxies are used in everyday applications like floor coatings, countertop sealants, potting, adhesive, all different sorts of materials. Epoxies are a specific chemistry that yields a rigid material with excellent adhesion and environmental resistance. Epoxy potting, coatings, adhesives, and underfills are used frequently in thermal management. Epoxies can be used in a variety of applications, like the ones below and as mentioned previously. 1K and 2K epoxies offer different properties and curing requirements, whereas 1K materials are typically designed for use with more advanced manufacturing processes. 2K epoxies are available for people with everyday equipment. Finally, we are proud to offer a variety of epoxy solutions for your application needs. And with that, we'll close for questions. But before we do, I just want to mention that the last session in our Thermal Management Virtual Academy will be next Thursday, March 4th, titled Urethane and Acrylic Properties. As always, feel free to use the QR code in the top right to sign up. Thank you, and we look forward to hearing your questions.